Hi, I'm Swarupa Sail, course instructor for fluid mechanics. In this presentation, we will go through fluid statics, pressure of fluid, pressure head and hydrostatic law. Fluid statics deals with fluids which are at rest. Static fluid has no shear force and only normal force is to be considered. Since there is no flow of fluid, there won't be any friction being offered by one layer of liquid on another layer. Hence, shear force will be equal to 0. And fluid statics is applied for pressure measurements in terms of fluid column height. So if we know the fluid column height, we will be able to find out what is the pressure at this particular height. We know that pressure is defined as force per unit area. Here the mass of a thin person is given as 70 kg and for a fat person it is 140 kg. Area of feet is 0.0343 square meter. In order to find out pressure exerted by the floor on the feet, we can use the formula force per unit area. Here force is nothing but the weight exerted and weight is equal to mass into acceleration due to gravity. Mass is 70 kg and g is 9.81. To convert it in terms of kilonewton, we will divide this term by 1000. Area of feet is given as 0.0343. So we get the value of pressure as 20 kPa. Similarly, we can find out pressure exerted on the feet for a fat person and it comes out to be 40 kPa. So when we compare both these values, we can conclude that the normal stress, which can also be called as pressure on the feet of a fat person, is much higher than that on the feet of a thin person. We will consider one more example over here. On this surface, we can see a sharp knife and a blunt knife which are applying the force F. Below sharp knife, area is small, whereas for a blunt knife, contact area is more. We know that pressure is equal to force by area. If area is less, pressure exerted will be more as P is inversely proportional to area. So here area is small, so pressure is more for a sharp knife. Hence we can say that the sharp knife exerts a large pressure on the surface due to the small area of contact. Whereas if we consider for a blunt knife, area is more, hence pressure will be less. So we can say that for blunt knife, pressure exerted is small as area is more. Coming to the pressure of a fluid, consider a fluid in a container. Since the fluid is at rest, it will exert force on all the contact surfaces. That means it will exert force at right angles to the sides of the container, to the bottom of the container and also on top of the liquid surface. Pressure is given as P is equal to W into H. Unit of W is Newton per cubic meter, which is nothing but the specific weight, and H is meter, that is pressure head. Meter and meter will get cancelled out, so we get unit of pressure as Newton per square meter, and it can also be equal to 1 Pascal, as 1 Newton per square meter is equal to 1 Pascal. 1 bar is equal to 10 raised to 5 Pascal, which is equal to 0.1 megapascal, and it is also equal to 100 kilopascal. Now we will find out what is pressure head. Here we can see a liquid in a container whose specific weight is W and height of the liquid is H. Pressure head, that is H, is the depth below the free surface of liquid at which we need to find out what is the pressure. So if we want to find out pressure at the bottom of the container, we will use equation P is equal to W into H, and H is equal to P divided by W. And this pressure head is usually written in terms of meter of water, meter of oil, or meter of liquid, and if it is mercury, it will be written as 760 mm of mercury. If we just write the pressure head as 5 meter, it is considered to be not correct. Hence, we need to specify the liquid under consideration. So, unit of pressure head will be written as 3 meter of water if this liquid is water, and H is equal to 10 meter of oil if this is oil, and so on. Now we will define hydrostatic law. It states that for a static water, the variation of pressure along the vertical downward direction is equal to specific weight of the liquid. Let W be the specific weight of the liquid and H is the depth measured from top surface of the liquid. And if we want to know pressure at point H, we will make use of hydrostatic law, that is variation of pressure, that is dou P divided by dou H, that is vertical height, variation of vertical height, which will be equal to specific weight. So when we integrate, we get dP is equal to W into integration of dH. Here pressure is varying and height is varying, whereas W is constant and hence it is taken out. Since there is a uniform liquid from top to bottom, we will take W as constant. And finally we get P is equal to W into H. So this equation will be used to find pressure at required depth. P also can be written in terms of rho. For that, let us consider a column of fluid. Now if we want to know pressure at the base of this column, we will use same equation, that is P is equal to W into H. But we know that specific weight is equal to density into acceleration due to gravity. So substitute W is equal to rho into G into H. So this equation can be used to find pressure if the density of the liquid is known. Now we will see how to draw pressure variation diagram. Consider a liquid in a container, and we know that since the liquid is at rest, it will exert pressure on the sides, on the bottom and also on the top. Now here, if we want to draw pressure variation diagram along one side of the container, then to begin with, we will draw a vertical line in order to represent one side of a container. Now for example, if I want to show how pressure varies on the left side of the container, we will represent it first by a vertical line. On top, H is equal to 0. And we know the equation to find pressure, that is P is equal to W into H. W is specific weight which remains constant for all the depths. So W is taken out and H on top surface of the liquid, whereas here it is 0. So since H is equal to 0, P will be equal to 0. So pressure on top surface of the liquid will be equal to 0. So we will mark point here to begin with. Later, if we want to know what will be pressure at depth 1 centimeter, we will again use same equation, that is P is equal to W into H. W here at 1 centimeter is same, so we will take out W into height is 1 centimeter. So we will get it as 1 into W. If suppose the liquid under consideration is water, we need to substitute specific weight of water. If it is mercury, then substitute value of specific weight for mercury. So now at depth H equal to 1 centimeter, we got the value of pressure as 1 W. So we will mark here as 1 W. Then next we want to find what is pressure of liquid at depth equal to 2 centimeter. We will use equation P is equal to W into H. W is constant into H is 2. So we will get P is equal to 2W at H equal to 2 centimeter. So we will again show H. For H equal to 2 centimeter, we will write the value of pressure. Then next, since height of the liquid is 3 centimeter, we will directly find out what is pressure exerted at the bottom of the container. So for H equal to 3, we will get P is equal to 3W. So we will mark here P is equal to 3W. So we got values of pressure at various depths. And we will draw a horizontal line to show the bottom of the container. And later we will join all the points starting from P is equal to 0 to P equal to 1W, then P equal to 2W, and finally P equal to 3W. And it's a linear variation. So this is how we need to draw pressure variation diagram for a fluid in a container. In previous slide, we had drawn pressure variation diagram on left hand side of the container, that is pressure exerted by liquid on left hand side of the container. Here this diagram shows that the fluid is exerting pressure on right side of the container. Here P is equal to 0 and here P is maximum. So P is written as rho GH because W is equal to rho into G. So P is equal to W into H, which will be equal to rho GH. And here it is mentioned that atmospheric pressure is ignored. So on top we will assume that there is no atmospheric pressure acting on the surface of the liquid. So to begin with, we will start with H equal to 0 so that P is equal to 0. But here in this diagram, we will consider atmospheric pressure. So we need to show the magnitude of atmospheric pressure. And down at the bottom of the container, total pressure will be atmospheric pressure, that is the magnitude of atmospheric pressure, plus W into H, that is rho GH. So total magnitude of pressure at the bottom of the container becomes P atmospheric plus rho GH. This figure shows the variation of pressure in a liquid. Consider that there is a liquid in this container which has got 3 holes, that is at A, B and C. Let H be the depth or height of liquid in this container, which is also referred to as pressure head. At C, we can observe that H is less and at A, H is more. From hydrostatic law, we have derived the equation P is equal to W into H. So, P is directly proportional to H. As H increases, P also increases. So, since at A, H is more, pressure of water at A is greater than that at B and at C. Hence, the lower hole A throws water farthest, followed by B and C. Thank you.